In the previous video, we have discussed about the parameters of a solar cell. And now let's see the data sheet of a photovoltaic modules. Right. Now in this slide, you can see the data sheet of a photovoltaic module. That BLD Solar. The data sheet of the company name is BLD Solar, and that BLD Solar has three different types of solar panel manufacturings, and one such is 240 watt peak panel, other one is 230 watt peak, other one is 225 watt peak panel. Now let's discuss about the BLD 240 watt peak solar panel. Now what are the things that will be there in a data sheet? The first point is peak power. What is the peak power? 240 watt peak. The second point is maximum power voltage, that is VMP, or maximum voltage VM, which is 30.18 volts. Maximum power current, or IMP, which will be 7.96 amperes. And next one is the open circuit voltage VOC, which will be 36.72 volts. And the last one, and the other one is the short circuit current, which will be 8.99 amperes. Up to this we have some idea. What is the peak power? What is the maximum power voltage? What is maximum power current? What is open circuit voltage? And what is short circuit current? Up to this we have already discussed in the parameters of a solar cell in the previous video. Now the other two parameters are cell efficiency and module efficiency. The cell efficiency is 16.5% and module efficiency is 14.66%. Right. So the cell efficiency is more than the module efficiency. Now in this video we will discuss what is a cell efficiency, what is a module efficiency, and why cell efficiency is more than the module efficiency. And one more thing is, if you can come below, temperature coefficient of short circuit current, temperature coefficient of open circuit voltage, and temperature coefficient of maximum power. These are the three more parameters which are of very big importance. In the next video we will see about these in explanation in detail, but let us understand what is this. Temperature coefficient of ISC means they have given plus 0.045% per Kelvin. That is, for every 1 degree Kelvin rise in temperature, the ISC will increases by 0.045%. Therefore, as temperature increases, ISC current increases, and for every 1 degree increase in the 1 degree Kelvin increase in the temperature, the short circuit current increases by 0.045%. And next one is the temperature coefficient of voltage, and the value given in the slides is minus 0.34% per Kelvin. What do you mean by minus? Decreases. That is, if I increase the temperature, the open circuit voltage decreases. I am talking about temperature. If I increase the temperature, the open circuit voltage will decrease. What is the meaning of it? So for every 1 degree Kelvin increase in temperature, the open circuit voltage decreases by 0.34%. And third one is the temperature coefficient of power, that is Pmax. It is at minus 0.47% per degree Kelvin. That is, it is also negative. That is, as the temperature increases, maximum power also will decrease. That is, for every 1 degree Kelvin rise in temperature, the maximum power will decreases by 0.47%. It is about the temperature. As the temperature increases, short circuit current increases, open circuit voltage decreases, peak power decreases. But as the solar radiation intensity increases, open circuit voltage increases, short circuit voltage increases, power also will increases. Right. As the solar radiation intensity increases, ISC, VOC and PM increases. As the temperature increases, ISC increases, VOC and PM decreases. This is the point which we need to understand. And further we will discuss about this in detail. Now let's talk about the standard test conditions. What are the standard test conditions? Right, while I was talking about the air mass in the first and second units, I already discussed about the solar panels standard test conditions. If I say the efficiency of a solar cell is 16.5% cell efficiency, or 14.66% is the module efficiency, at what conditions? At standard test conditions. What are those standard test conditions? So STC is called the standard test conditions, is an industry-wide standard to indicate the performance of a solar module. So solar modules can be prepared in Guntur, solar modules can be prepared in Hyderabad, solar modules can be prepared in China, solar modules can be prepared in France, solar modules can be prepared in America. But we need to in order to calculate the efficiency of those panels, we should take some standard conditions. For example, why I have to take standard conditions? The temperature in India, China, America is not same. They may be different, but therefore I need to take a standard temperature of 25 degrees centigrade, as well as light intensity also will be differing. In America, in some places the climate will be very cool. Say for example, in India, in Kashmir, the climate is very cool. The solar radiation will be very less. But whereas in Guntur or Vijayawada or Hyderabad, the solar radiation is very high. So we need to take a specific solar radiation, and that is the reason why I am taking 1 sun. That is 1000 watt per meter square is called as 1 sun in solar industry terminology, and air mass is 1.5. These are the 3 points which I need to keep, which I need to take while calculating the efficiency of a solar cell. Now if I take these 3 points same, whether I manufacture the panel in Mumbai, Delhi, Calcutta, USA, California, Canada, Australia, wherever it may be, then the efficiency will be same throughout the world, because I am taking at this particular conditions, right? And as we already know, what is a formula for air mass? Air mass equal to secant theta z. Theta z is zenith angle. So zenith angle equal to secant inverse of air mass. Air mass is 1.5. So theta z is secant inverse of 1.5, which will be 48.2 degrees, which is also I have discussed. So the zenith angle corresponding to standard test conditions is 48.2 degrees. Fine. Next one. Now let's talk about the cell efficiency. What do you mean by efficiency? Efficiency is nothing but output by input. By this time you might be knowing the meaning of an efficiency. Output by input. Let me take an example to make you understand what is an efficiency means. Say for example, a student is there. There is a subject, he has to write an exam for that subject. The total marks are 100. That is the input marks. The question paper is set for how many marks? 100 marks. That 100 marks is the input. But what is the marks he will get in an exam? He may get 10 marks, he may get 20 marks, he may get 30 marks, he may get 70 marks, he may get 90 marks, he may get 100 marks, depending upon the student. Now how can I tell the efficiency of a student? Efficiency is nothing but output by input into 100. So what is that? So efficiency equal to the marks obtained by the student in an examination divided by total marks for which the exam is kept. That is, the input is the 100, whereas the output is, say for example, a student got 70 marks. So 70 is the output and 100 is the input. So what is an efficiency? 70 by 100. So into 100. So the student is 70% efficient. So he knows about that subject only 70%. If he get 100 of 100, it is nothing but he knows completely about the subject. That is by input is equal to output. It is what is called an efficiency. Now the solar cell efficiency is also the ratio of output power to the input power. What is the output power? Electrical power. The output of a solar cell is electrical energy. But what is the input of a solar cell? Solar energy. So therefore the ratio of output electrical energy to the input solar energy is called the solar cell efficiency. Therefore the efficiency of a solar cell is given by P out by P input. P output is the maximum power that can be coming out from a solar cell, and P input is the solar input power. What is the P max? Maximum power drawn by the solar cell is V maximum into I maximum, which is one of the parameter of a solar cell. P max is nothing but V max into I max. And what about the solar input power? We know the solar radiation intensity. What is the unit of solar radiation intensity? Watt per meter square. Therefore the solar radiation intensity is watt per meter square. That is, say 1000 watt per meter square. That is 1000 watts of solar power is falling on the solar cell per meter square area, right? And what is the area of a solar cell in meter square? If I multiply that solar intensity with the area of a solar cell, I will get the total power falling on the solar cell. Say for example, the area of a solar cell is 2 meter square. The solar radiation intensity is 1000 watt per meter square. So per meter square, 1000 watts are falling on the 1000 watts of solar power is falling on the solar cell. Now the area of the solar cell is 2 meter square. So 1 meter square 1000 means 2 meter square 2000. Therefore, solar radiation intensity into solar area of the solar cell in bit. So watt per meter square into meter square cancel, you will get in terms of watts. Right. So P output by P input. P output is in terms of what? Vm into Im means what? Watt. Now P input is what? Watt per meter square into meter square. It is also in watt. So both the units, both the numerator and denominator should be in same unit. Therefore, Vm into Im is the output power divided by what is the input power of a solar cell? Solar cell radiation intensity, that is Is in into area of the cell. So now what is the efficiency of a solar cell? Vm Im by Isc into Is input into A cell. Now in the previous case, from this data sheet, we got the efficiency of a solar cell as 6.5%. How it came at 6.5%, we will see it now. Right. So in this cell, let us take how many cells are there in this solar cell, in this solar module. A module consists of so many number of cells. I already discussed this in the last unit itself. The cells connected in series is nothing but a solar module, right? So this solar module or a panel consists of, you can see in this data sheet, you can see the cells column 60 into 10 pieces, that is 60 cells are connected in, there are 60 cells. 6 into 10 pieces means 60 cells. 6 to 10 means 60. That is 60 cells are connected in series. And what is the area of each cell? 156 millimeter into 156 millimeter. The area of each cell is 156 millimeter into 156 millimeter. So what is the area of 60 cells? 60 into 156 millimeter into 156 millimeter. Right? Now let's see. The number of cells is 60 cells. So area of each cell is 156 millimeter into 156 millimeter. What is 1 millimeter is equal to 1 millimeter equal to 10 to the power of minus 3 meters. Right. So 156 into 10 to the power of minus 3 will be 0.156 meters. Therefore 156 millimeters will be equivalent to 0.156 meters into 0.156 meters. If I multiply 0.156 into 0.156, I will get 0.0243 meters square. It is the area of a single cell. Now what is the area of cells in the panel? There are 60 cells and the area of each cell is 0.0243 meters square. So area of 60 cells is 60 into 0.0243 meters square, which will be 1.46 meter square is the area of the cells in the solar panel. Now let's calculate the efficiency of a solar cell. So efficiency of a solar cell is nothing but output by input. What is the output? P max by P input. What is P max? V max into I max by P input. Now what is P input? Solar radiation intensity. What is the power? Solar power. Solar input power is solar radiation intensity multiplied by area of a solar cell. What is the solar radiation intensity? Standard solar radiation intensity is, it is a 1 sun, that is 1000 watt per meter square, into what is the area of a cells? As we already got it, 1.46 meter square. So 1000 into 1.46 will be 1460 watts, which is the denominator, is the solar input power. What is the output power? That is electrical power. P max is nothing but Vm into Im. From the data sheet, what is PM? VMP is nothing but 30.14 volts. And what is the maximum power current? IMP is nothing but 7.96. If I multiply these two, what I will get? 240. Therefore PM is nothing but Vm into Im, that is 30.18 into 7.96. Straight away you can take 240. Therefore 240 by 1460 will into 100 will give me 16.5%, which is the efficiency of a solar cell. Now coming to the next parameter, module efficiency. Now what is this module efficiency? 14.66%. That is, the cell efficiency is greater than the module efficiency, or otherwise the module efficiency is less than the cell efficiency. Now let us calculate the module efficiency. What is a module? We will see. Now let us see. solar module efficiency. The efficiency of a module is generally less than the efficiency of a solar cell. From the data sheet we have already seen that the efficiency of a solar cell is 16.5%, whereas the efficiency of the module is 14.66%. Why? We'll see that. So efficiency of a module is nothing but output power by input power. Likewise, output power is nothing but maximum power by input power. Maximum power is Vm into Im by input power. Maximum power is Vm into Im. Solar input power is solar radiation intensity is 1000 watt per meter square into, in place of area of the cell, now we have to keep area of the module. Now let us see it here. Now let's see the diagram of a solar panel over there. In that panel you can see the solar cell is not a perfect square. At the edges it was cutted. Right. So now you can see that white diamond color spaces. The diamond color spaces is what? It's the empty space. When sunlight falls on the diamond color space, will that diamond space convert the solar energy into electrical energy? Obviously no. Whenever the sunlight falls on the black portion of a solar cell, then that solar energy will be converted into electrical energy. But whenever the sunlight falls on that white spaces, then that solar energy will not, the solar energy falling on that white spaces will never be converted into electrical energy, because there is no solar cell in that space. Therefore area of the module means in that module we will get spaces also. Therefore area of the module is nothing but area of the cells, solar cells, plus area of the spaces, area of the white spaces. Therefore now you can tell me area of the module is more or area of the cell is more. Area of the cell is less compared to the area of the module, because there are 60 cells. We already calculated the area of the cells in the panel is 1.46 meter square. But in that 1.46 meter square, the white spaces area is missed. Now in order to calculate the module area, we need to add that white spaces area also to the solar cell area. That is, in the previous case we got 1.46 meter square as the solar cell area of a solar cells in the panel. So in order to calculate the area of the module, we need to add the area of the white spaces to this area of the solar cells in the module. So when I add that, the area of the module will be more compared to the area of the cell. So whenever the area of the module increases, the denominator value increases. Whenever the denominator increases, what happens to the numerator is constant, Vm into Im. The denominator is increasing, numerator is constant, and what happens to the fraction? Decreases. Therefore the module efficiency will decrease. That is, efficiency of a cell is 16.5%. Efficiency of module will be less than the efficiency of a cell. In the next video we'll see what is the fill factor. Thank you.